Very good day to all of you. I'm Shivansh Srivastav. My roll number is E21B125, and today I'll be going to present my course project on color coding and subset sum. So, color coding, I had chosen the topic of color coding because I found it really interesting after reading some of the research paper, and today I'll be going to share my findings of these research papers with you. So the outline of today's presentation will be like, I'll be talking about the k-path and k-cycle algorithm, and then I'll move to the subset sum problems, and then I'll go through some of the open problems which I found during while researching about these papers. So the k-path and k-cycle algorithm is an NP-hard problem, and which is on paper quite simple when written, but solving it has proven to be difficult. But color coding has given us a very nice solution regarding it, which is quite feasible also. So let's go to the problem definition of k-path and k-cycle problem. So the problem definition I told you was really simple, and it goes on like this, like whether a graph has a simple path of length k or whether a graph has a simple cycle of length k. Let's think about what a simple path and simple cycle actually is. It is a path in a graph when we travel k number of edges, but we don't visit a vertex twice. So that's known as a simple path. And similar goes for a simple cycle, that we find a cycle in a graph such that the k vertices in that cycle are all unique and distinct. So to solve it, we will use the color coding algorithm. But before that, let's use the naive algorithm of random orientation and see, like, without any particular approach, what's the time complexity it's giving and how we can improve upon the same. So, and this whole thing has been passed on to the paper of Ellen Usher and Zwick, which was published in 1995. So let's go to the random orientation algorithm for this k-path and k-cycle problem. So these were the two results which was published in the paper. The first result says that the length of the k-cycle, like a k-path problem, can be found in the expected time of k plus 1 factorial times the number of edges which is present, and the k-cycle can be found, if present, in k minus 1 factorial times log 2 times v power w of the expected time, where w is the matrix multiplication coefficient, which turns out close to be 2.2376. So we'll first look at the k-cycle k-path problem. I'll just move my face a bit so that it would be easier for you to see. So as the theorem 1.1 suggests completely, that the expected time to find a k-path is O of like k plus 1 factorial times c. So to do that, let's start with a random permutation of all the vertices which we have for a directed graph. After that, what we'll do, we'll select only those edges in which, so we'll iterate through all the edges in the directed graph, and then we'll select only those edges and in the undirected graph, and then we'll select only those where pi of u is less than pi of v, means the first vertex is coming before the second vertex, to make the undirected graph to a directed one. Why we are doing so? Because to find a simple cycle, it's important for us to have a directed acyclic graph, and this part of this step is completely doing that. After that, the directed acyclic graph, the DAG which we'll get, will check if the longest path exists there or not. Now, if we look closely, the running time of this, the probability of finding a directed acyclic graph in this sense is 1 by k plus 1 factorial, the probability of finding that. So expected number of time which we have to run the problem is, run the algorithm will be k plus 1 factorial, and as on each step we have to iterate to all the edges at least once, so its expected runtime will be k plus 1 factorial times c. So the proof was pretty straightforward for random orientation, but we can see like k plus 1 factorial is actually quite a huge number, and it clearly goes blasts off when the k reaches some finite values. We'll see how we can improve upon this with the help of random coloring algorithms. But before that, let's also see the random orientation algorithm for the k-cycle problem. So now I'll be moving towards that. So for the k-cycle problem, we'll do the following. First, we'll create a directed acyclic graph in a very similar manner as we did for the k-path problem. And after that, we'll form an adjacency matrix for the new graph G star, which we have made, and let's denote that adjacency matrix with A. After that, what we'll do, we'll raise the power of adjacency matrix to k minus 1. And so what it will give? It will give us all the possible simple paths in a G star graph such which have the length of k minus 1, because that's the property of the adjacency matrix. And now after that, as we now have got the path of k minus 1, we'll check like whether for any of this path the endpoint and the starting point has a common edge in the original graph G. Now if we have such a point, it becomes pretty clear that we have a cycle of length k, and so that's a pretty algorithm. Pretty simple, isn't it? So the runtime of the algorithm will be k minus 1 factorial at the beginning, as we have seen in the previous part. Along with that, as we are raising the matrix to the power k, we can use binary exponentiation for that. So that will just give us a factor of log k over there. Along with that, to multiply two matrices, where we are multiplying for raising the power, we just need v power w of the time complexity, where w being 2.2376, which has been the most efficient algorithm for matrix multiplication. So, and hence the result which we have sought, we have achieved that. So these algorithms were pretty naive for random orientation. So now we have to improve upon them. How we can improve upon them? We will improve upon them by looking at the algorithm of random coloring. So how random coloring is actually useful for us over here? Let's discuss about that. So random coloring will help us to find different type of pattern in a graph actually in this particular case. What we'll particularly do, we'll color the graphs randomly and color the vertices of graphs randomly, and then with the help of dynamic programming, we'll try to find whether k path or k cycle exists in the graph. Finally, we'll receive two of the result which I have mentioned over there as theorem 1.3 and theorem 1.4. Let's go through them once. Theorem 1.3 states that in a graph, a path of length k minus 1 exists, then it can be found in just 2 power k dot v. V is the number of vertices in the graph, which is the expected time for it. And for undirected graphs, it becomes 2 power ok dot e. And theorem 1.4 says, like if we want to find the k cycle in a graph, it can be found in 2 power ok dot ve or 2 power ok times v power w. So these two improvements are pretty strong when we compare the algorithm to the random orientation algorithm. Now let's see how it's actually proved. As we go for 1.3, we'll first consider a new vertex x of the graph, and we'll connect all the other vertices of the graph with that point. And then we'll try to find a length k. We'll try to find the length k of the graph with the help of dynamic programming, whose state are as follows. A vertex v will be at a distance I from s. That's the state which we are defining, and there is a corresponding coloring of the graph where the kci numbers of colors which you can use to color those I particular length of the graph. After that, we'll see that what are the neighbors of the vertex v is actually are. So we have neighbors of v, let's say u, and the coloring of u doesn't lie in any one of the possible coloring which is present. So what we are going to do, we'll just add the u, and we'll just mark u with the type plus 1 and add the color of u to the original coloring which is present with us. So it will give us the next step. So as we continue to the every last of the vertex, if there is a path of length k, we'll reach it at the end, and just to do that, we'll require the 2 power ok dot v time steps. So that's actually pretty strong result, and the calculation for the number of steps which you require is pretty straightforward too. So that's actually a really beautiful result, because it helps us to find a k path in a graph in just 2 power k dot v of the time step, while the random orientation was taking k factorial type of time. So it's pretty strong when it's compared to that. Now, if we have to search a similar thing for the k cycle problem, what we are going to do is we'll partition the graph randomly in two parts of equal sizes. Now, we'll create a new graph G1 which has the color of all the points of the C1 graph, and G2 which has the color like for all the vertices which is present in C2. After that, for each particular G1 and G2, what we'll do, we'll try to find a single path of length k by 2 minus 1. Why we are doing this? Because when we have two paths of k by 2 minus 1, if we can find a common edge between the two paths of the cycle, we'll get by k minus 2 minus 1 times 2 plus 2. So that's simple thing which help us to calculate a k cycle of the algorithm. To move along that direction, what we'll do, we'll create a adjacency matrix B, which have the all edges from G1 to G2. Now to finally get a path possible, we'll take odd over all A1, B and A2. And if the path will be present, that order will give us a 1 at any point. And to show the calculation of how much it's working, it will actually like 2 times n of k, means for the k cycle that will equal to like 2 times n of k by 2 plus 2 to the power k times c k by 2. Now this particular thing is a recursive relation which upon calculation will again give us 2 power ok, but as we have to run the algorithm e times for each of the subset problem, it will give us a time coordinate 2 power ok e. And then there is a vertex, and the vertex multiplication will give us the factor of v power w. So as we can see, the randomized algorithm of color coding is actually really helping us to find the k path and k cycle algorithm, which will be much better than the naive algorithm which is present with us. If we move forward, we'll also find that randomized algorithm of color coding is actually pretty strong, because it also helps us to de-randomize the algorithm pretty easily. And for that, we'll be using k-perfect hash families. So what k-perfect hash family is? Let's go through that. It is a family of hash function which is from n to set k, and is called k-perfect if there is a subset which is of n, and such that when it's mapped to k, there is a one-to-one function towards ds. So that's the k-perfect hash family. The construction of k-perfect hash family has been explicitly given in the paper of 1919 by Janet and Spalger. So with the help of that, we can construct that k-perfect hash family, and when we'll implement that algorithm, we'll find that we just have an extra factor of log v in both of the k path and k cycle algorithm, which is really strong to help us to de-randomize the complete algorithm. And that has been the beauty of the color coding algorithm in all its application, because de-randomization of it becomes really easy with the help of hash families. So that was all about the result which I got from the Uric AZY paper from 1995. Other than that, there is one more important and what I can say interesting application of the color coding randomized algorithm. That being said, that application is finding the subset sum. So subset sum problem is again pretty basic problem, but is again NP hard, and it's really difficult to solve and to get a polynomial time solution without a proper bounds. So let's go to the problem definition first. The problem definition says that if we have a set of positive integer and have a target sum t, can we find a subset from that set whose summation will give the value equal to t? There has been a dynamic programming way of solving this problem, which is pretty straightforward, with a time complexity of O of nt and the space complexity of also O of nt. Along with that, we'll see a randomized algorithm based on color coding, which is making it close to linear time algorithm with O of n plus t with very small one-sided error of delta. So to move forward, let's first see how dynamic programming algorithm actually works in this case. The algorithm is pretty simple. What we'll be doing is we'll have S be the set of the number, T is the target sum, we have taken that. We'll create a 2D Boolean array of size n into t plus 1, where t plus 1 being the column. And we'll mark AR of the array, the first row, and the S of 0 to be true. Then we'll iterate and to the next row. We'll iterate through all the values of t and check if the particular column minus the S of I is 1 in the previous row, then we'll mark that particular cell as 1. And we'll go through all the rows in this method. If at the end we'll find that the lastmost cell AR of n minus 1 of t is equal to 1, then we can say that we have a valid subset sum. We can find this subset sum very easily in O of n time with the help of backtracking. This algorithm in total, as we are moving through all the cells of the array, is simply taking the time complexity of O of nt and a space complexity of O of nt, which is comparatively very huge when we compare to the what we are getting from the algorithm of random coloring. Now let's look at how the random coloring algorithm actually works. So the whole thing of random coloring algorithm for subset sum is actually quite complex and requires quite a number of techniques. Some of the main being the subset computation, which basically use the random coloring algorithm, and it gives us an bound which of t of log of t, which is not linear but is in the t of log of algorithm. We can improve this thing particularly with the help of fast Fourier transform, and along with that we'll also use color coding to find the sums generated by small subsets. So these were the two important parts where the color coding algorithm was being used in the subset sum problem. Now let's look at what the basic idea of the algorithm is. What we'll do for each element in Z being the subset completely, we'll color each of them in the k square possible colors which is present with us. So after coloring them, we'll partition each of them based on the color. So Z1 will have all the elements which are colored by the color 1. Similarly, Zi, and as we go on, Zi is the set which has all the elements which is colored by the color I. Now we'll define a set Y which has only intersection with all the Zi's, just one element or a zero element, and a subset sum will be the summation of Yi. We'll repeat this process quite a many of time so that we can get different values of Yi, and after that when we put bounds upon it, we'll find that it just depends upon the efficiency which we want of the algorithm, which will be 1 minus delta. As we can see, this whole thing will become pretty similar to be like the k square bins problem, where we have to fix k ball into k square bins, and that probability will be less than 1 by 4. Upon doing all these things, actually we'll arrive at three particular lemmas for the subset sum problem with the help of color coding. At present I won't be giving the proof of these particular lemmas, but it is worthwhile to go through them once. The color coding algorithm will give us a time complex t k square log t and log 1 plus delta. So this complete thing is actually k square is very small. It's we can consider as a constant, and log t, as I told, it gives us a complexity of t log t, but by fast Fourier transform we can get it down to the t. The log 1 by delta is actually based on the type of efficiency which we required. And the whole thing is coming with a very small probability of 1 minus delta. The other thing, lemma 2, is actually an improvement upon this by the concept of the split layering. So in this thing, I'll get the subset sum in like t log cube of L by delta, where 2t by L is the largest possible number in the split coloring. The lemma 3 is actually providing us with a Chernoff bound of the same thing, as saying that we can find the subset sum with a very small probability of delta by L, and that's it. So when we combine all these three results with each other, we'll arrive at a solution like where we can get the subset sum of the subset which is equal to value of t with the help of color coding algorithm in just n plus t log t algorithm, which is quite efficient when we compare to the dynamic programming algorithm of OINT with just an one-sided error probability of delta. So as we can see in both of the cases, the color coding algorithm has really helped us to boost the time complexity of the two NP hard and difficult problems, which is quite amazing in its own sense. It is also helping us to find the solution of the problem with a very small error probability, especially in the case of subset sum. So color coding algorithm has been like pretty useful in this type of systems where we need to find some kind of a pattern or a motif in a network. That's why we'll see like when we search upon the application, we'll find a lot many places such as the social networks, the computer network, the subset sum problem is actually quite very useful. Along with that, when I was researching upon this whole thing, I came across some three applications, three open problems in the field of subset sum, which I found quite interesting. The first one being, is there a polynomial time algorithm for deciding whether a graph contains a path of length, say log square v, which can be completely random in itself. The second one, can the log v factor appearing in de-randomization be omitted? See, subset sum problem has a color coding problem has really powerful, what I can say, the use case in de-randomization, because it's really easy to de-randomize color coding algorithm, as we have seen in the k path and k cycle problem. But as we see at that point that we got an extra block t term over there. Now can we find an algorithm which can omit that thing? I found this pretty interesting. The other being, if the problem of deciding whether a graph given g of v comma e contains a triangle as difficult as the Boolean multiplication of two v cross v vectors, pretty straightforward in its sense. So the whole thing, when I was researching on the subset sum,